welcome to this week's problem session. Hopefully it'll be pretty quick. This week's homework, I'm mainly gonna just spend some time on the dual input describing functions and dither. Next week I'll go over a midterm from last year, and so because that's the day before the midterm. So yes, let's get started. The first problem in this homework is, so we're talking about designing a compensator for a nonlinear system. Let me just draw it out. Let's see. So you have two specifications for this, for your controller. The first one is that there will be no limit cycle when r of t is 0. So this just means that on your Nichols diagram that your plot of your linear part does not intersect with your plot of -1/n. So that's pretty straightforward. The second requirement is that the dead zone referred to the error. This is the error. I'm going to call this x. This. So the dead zone referred to the error is less than 1. So what this means is that if we're talking about the dead zone and the error, we're really talking about when the system is in steady state and not any of the transient responses. So we want that when we're in steady state, the error that we get put through our compensator, right? And then, so we arrive at the input. It's over here. That, so we're in the dead zone, so we're not really moving very fast. We're just kind of sitting around in there, and so that this value delta corresponds to when the error is less than 1. So I write that as delta is our compensator. So s equals to 0 because it's DC, and our error at t equals to infinity. So DC. And since it's given the problem that delta is 5, so this basically translates to that the DC gain of our compensator has to be greater or equal to 5. If it's delta. So that's what that means. Just remind ourselves what the describing function for deadband is. So we have n equals to 4m to d over pi a root 1 minus delta over a squared for a squared. Okay. So basically with this information we can go ahead and draw our Nichols plot of our system and see if it intersects. So first of all, what does the describing function look like on the Nichols plot? Well, we can start off with, so if we had our Nichols plot, okay. Let's call this so the smallest value of a we can have is when a equals to delta, right? So when a equals to 5. So, and what is that? Well, this goes away, so n equals 5 is 0. Now we increase a. What happens when a is infinite? Well, this is 1, but this is 1 over infinity, so that's also going to be 0. So when we put this over to 1 over n, so that's going to be infinite, and this as well. What's the phase? Well, the phase of n is 0, which means the phase of negative 1 over n is going to be negative 180 degrees. So we're going to start off somewhere in infinity, and then we're going to come back down, and then at some point we're going to go back up. That's essentially what that looks like. Now, how do you find this point? Any ideas? Yeah, well, the max. Yeah, the max of n. What's the max of n? Put it in MATLAB. Yeah, exactly. So we could take the derivative. So if you want to find, not that you have to do this, it's kind of interesting. You can take the derivative with respect to a. So I set that to 0. So in this case, we end up with something like 40 over 5. So now you put it in MATLAB. But just for general interest, this point over here corresponds to an A star. So we get of 5.2. So basically, this point over here is something like 0.779. But you'll probably do this in MATLAB. So So now we have, this is our plot of 1 over n, negative 1 over n, and we have our L. Your L is going to look like, it's going to look something like this. And so this is probably with k equals to 5. So if you set k equal to 5, and if you just say that, I'm just going to put a straight gain in there, you'll see that it's probably not going to work. So you're going to need some kind of a compensator that kind of just makes it do that. And this is all E105, E205 stuff. So it's very similar to a previous homework question, actually. We're good? All right. Number 2 asks you to derive one of the DIDFs in Appendix C of Kelvin-van der Velde. I'm not going to go into it. You could choose any one you want. The Appendix C is uploaded onto coursework, so you should be able to find those. Number 3. Dither. Alright. So you have a system, you build it, you figure out that it's got some Coulomb friction, and you like the original design you had, so you don't want to change that, you want to add dither to make it better. So your real system has looks something like this. So I think I mentioned in the previous email that just set m equals to 1. Here's our u. Okay. So for the first part, you're just plotting the response of the ideal system with and without friction. It's easy enough. So the second part, it asks you to, we want to choose the dither frequency and the dither magnitude. So our u dither is going to look like, something like a magnitude AD cos omega d. Right, so we want to choose the omega d and the AD. And we're going to use our IDIDF to do this. And I think it's given that y equals to 1. So magnitude equals 1. So the first thing we'll do is we'll work with the frequency. So we have our ideal system, and we want to make, so let me just write down the assumptions for IDIDF. We want our dither frequency to be at least 3 times the bandwidth frequency of our So this is just the frequency at which we want to change y, right?
Y is constant.
So we're controlling, let's say we're tracking this at some, it could be a slowly varying function. It doesn't have to be always constant, right? But what we're saying is, if we had the ideal system, right, with just s plus 1 and just like 1 over s squared. Right, we want to figure out at what frequency of input can we still, track this input with our output, to our satisfaction, which is essentially, what is the bandwidth of this closed loop. So that's our first assumption. The second assumption is that A. So over here, this is the input to our nonlinearity. This is A plus B cos omega. We want A to be at least 3 times the size of B at the entrance of our nonlinearity.
The input entrance that's on the entrance of nonlinearity is not necessarily the same as input A on the dither.
Ooh, wait, sorry. Wait, hold on. Yeah, so this is different from this.
Okay.
Yeah. Yeah. Wait. This is B plus A. So with these assumptions, let's first figure out what the bandwidth is. Right. So to do that, a couple things you can do. The first way is you could plot the closed loop Bode plot, and then figure out where it, where the magnitude reaches, so minus 3 dB. So that's basically 1 over root 2, or 0.707. Could also just write it out. So if we do the transfer function from yc to y, we get, just for the ideal system, right, so we get that. So the bandwidth, we're basically looking for when the magnitude of this at the bandwidth equals to 1 over root 2. And we can expand that out and get J omega bandwidth over so it looks like something like that. And you can just solve this for omega bandwidth. Or you could draw the Bode plot, might be easier. So once we have that, once we have this, then we know what our dither frequency should be, right? So once we find the bandwidth, we can find the minimum dither frequency, right? So that's good. So we got one thing. Now let's try to figure out what B should be. Okay. So we gotta basically figure out both A and B, and then, well, first we figure out B, and then we can use the assumption to solve for A. Once we have A, we can figure out A dither. So that's kind of the plan. To find B, so when we're talking about B, that's the kind of DC constant input. We want to look at the low frequency of the system. So what we could do is we could redraw our block diagram, just shuffling things slightly so that we get our output where we want it. So that's so this is our X. Let's say that's X. So when we're considering the low frequency response, we can, for now, ignore the dither. And what should this block do? What do you think? Which?
The bias term.
Yeah. So you can put NB here. So the great thing about the ID-IDF is it allows us to completely separate our analysis. And when we're looking at the low frequency system, we can just use NB, and when we are looking at the dither frequency, we can just use NA. So that's the easy part. So when we do this, recall that NB is 2m over IA. And A is 4m over IA. So this is X, and the magnitude of X is just B, right? So now we got a nice block diagram from an input to an output. Let's get the transfer function of this, and then we can see what the highest gain is, and so then solve for what the maximum B would be. So if we just work that out, we get X over YC. If you work through the algebra, you get something like this. If you just look at this transfer function, what happens at really low frequency? So when S goes to 0, this goes to 0, so this whole thing kind of goes to 0, right? What about really high frequency? So when S goes to infinity, right? What we could do is, you could do a thing where you divide top and bottom by S squared, and that would cancel out all the other terms, and you're left with 1 over 1. So when S goes to infinity, this thing goes to 1. So what Professor Rock talked about in class is you have this transfer function. You can plot the response for various A values and see, so YC. So if you take the magnitude of all of this, right, then YC is just 1, right? Just 1, and the magnitude of X is just B.
This is the plot he's talking about.
Yeah. So we're trying to find what the maximum B would be would come out of this. Right? So if we plotted this for a bunch of a values, you'll see that they're not so different, and essentially, like, we've already done all the analysis. So like the low frequency to high frequency, and you're gonna end up with something like your maximum B is somewhere around 1. Okay, but plot it and verify it for yourself. So that's good. So now we have B. We can use this to find A, right? So the minimum A is just 3 times the B. And once we have A, we can use that to find A dither. So when we do this, we gotta now switch gears to, so instead of the input of Y, we're gonna have the input of U dither, and then we're gonna just redraw the transfer function a little bit. If you can, if you can just work it out without redrawing it, that's fine, totally fine too. I'm just gonna draw it to make it a little bit more clear. So again, so now this is a transfer function from UD to X, right? So before our UD would come out here, right? And since now we're looking at the dither frequency, I'm gonna replace the nonlinearity with the describing function NA. And again, we'll write the transfer function from UD to X, and we know that the magnitude of X in this case is just A, right? So that goes into A. So what we could do is UD, end up with something it's very similar to the last one. So when you take the magnitude of this, just end up with A over AD. Right. And I won't write it out. But and you want to solve this at your dither frequency. Right. So sub in S for J omega dither. And so you'll get an equation. We know what A is, right? So now we should be, we have everything and we can just solve for AD. That's pretty much it, right? You got your AD, you got your omega D. Plot it, simulate it. And, oh yeah, the question also asks you to use a higher frequency 10 times as fast. So
that's not changing anything. Right.
So your omega d is going to change. So yeah, omega d is going to change, but this is going to be the same. A is going to be the same, but AD is going to change because that depends on.
Okay, so it is given that you increase the dither frequency, also change the magnitude of the. Yeah. Okay.
So the big takeaway is when we're using IDIDF, we can completely separate the faster dither frequency from the DC kind of constant input by using these two describing functions. Any questions? All right. Well, thanks.
Thank you.